Hi, Doctor. We are Group 16. And today we're going to present our group assignment 2. Our topic is Pythonic sort. And these are our group members. Now I will do a short briefing about our hardware implementation of an 8-element 4-bit parallel Pythonic sorter. So in applications like the network routing and digital signal processing, traditional software route sorting is simply a bottleneck where you need a high throughput, low latency hardware solutions. To solve this, we designed a RTL system that takes a 32-bit unsorted vector and process it into a perfectly sorted array in exactly 6 deterministic clock cycles. The major architecture highlight of our design is a strict decoupling of the data path unit and the control unit. By isolating the parallel, compare, and swipe elements from the state machine, we were able to maximize the clock frequency, guaranteeing predictable timing and highly optimized physical resource utilization. So now let's dive into the details of how this architecture works.
My name is Liu Zhonghan, and I will be explaining about the data path unit. Our DU consists of a few parts. First, we have the input selection multiplexer on top. When load data equals to 1, it accepts the external 32 bit, and when load data equals to 0, it would process the loopback of the feedback bus. And then the data would be sent to our register file. It consists of 8 distinct registers which are R0 to R7, and each register is 4 bits wide and it's 32 bit in total. It's used to store and send the data to our input routing matrix, and this block handles the shuffling required by the Pythonic sorting algorithm. It uses a 3-bit selector to take the 8 outputs from the registers and arrange them into 4 separate pairs of wire. And then we have the compare and swap blocks CAS1 to CAS4. It always compares if input A is bigger than input B, driven by direction bit 1 through direction bit 4 from FSM. It it would also output the smaller of its two inputs on the 4-bit low wire and the larger on the 4-bit high wire if ascending sort is active. And then lastly, we have the feedback bus. It gathers the 4-bit low outputs and 4-bit high outputs from all four CAS blocks and concatenate them back to the input multiplexer and wait for the next clock edge. My name is Liu Zhonghan. And next, this is our control unit. Our CU has 9 distinct states. And first, we have idle and initial. They wait for user start command and loads the initial 32-bit data in. And during stage 1 through 6, the CU steps through the Pythonic sorting sequence by dynamically changing our 10-bit control vector on every clock cycle. It adjusts the selector set step bits to shift the hardware between neighbor to neighbor, 2-element apart and 4-element apart wire routing paths, and at the same time it toggles the 4-direction bit lines to command the CAS blocks to sort either ascending or descending. This allows us to reuse the exact same physical wires and comparison blocks to shape the data stage by stage. And lastly, we have the done stage, which asserts the done fact 1 when the system is done. And next, this is the integration of our data path unit and control unit. And this is the integration.
So now let's talk about the data path module. But before that, we will start with the CAS unit, which stands for compare and sort. Think of this as like a tiny dedicated sorting machine for just two numbers. It takes in two 4-bit values, A and B, along with a direction signal, which is DIR. If DIR is 1, it sorts them in ascending order, pushing the small number to the low output and the larger number to the high output. If DIR is 0, it flips the logic for descending order. So it does all of this instantly using a simple combinational logic. So now onto the data path unit. So this is where we use those tiny CAS units to store a whole array. So first we have 8 4-bit registers, R0 through R7. When the load data signal is high, we pull in 32 bits of raw data and divide them into 8 separate numbers. Then the routing matrix happens. Because we are sorting 8 numbers, we instantiate exactly 4 parallel CAS units. That means in a single clock cycle, we can perform our comparisons, 4 comparisons simultaneously. Notice the case block. A Bytonic sort for 8 elements require exactly 6 stages. So depending on which stage we are in, the multiplexer pairs up different registers and feeds them into our 4 CAS units. So for example, stage 1 compares adjacent neighbors, while stage 4 compares items that are like 4 spots apart. And finally, we look at the bottom of the code, which is the unrouting matrix. So once the CAS units finish their swaps, this logic multiplexes the newly ordered numbers back into the feedback bus. So on the next clock edge, those numbers are saved back into R0 through R7 for the next stage. After 6 ticks of the clock, the data is perfectly stored and ready to be read from the data out wire. So now let's take a look at the waveform simulation to see exactly how the data path you need for the Bytonic sorting process starts from beginning to finish. So the simulation starts when the active flow reset signal, which is reset n, goes high, bringing the system out of each initialization state. So right after the reset, our initial unsorted data, which is 78654321, is sitting on the data in line. With the register write enable put high, this raw data flows directly into the register inputs and is latched into the system's register on the next clock edge. You can see this reflected instantly in the data out signal. So once the data is loaded, we pay attention to the SEL step signal at the very bottom. It counts up sequentially from 1 all the way up to 6, driving the 6 distinct stages of the sorting algorithm. As this step counter increases, we can see how the direction control signals DRR1 through DRR4 toggle on and off. These are acting as master conductors, which tells the parallel CAS units whether they should sort their specific data pairs in ascending or descending order for that exact stage. So if we focus on the feedback bus and data out signals, we can trace that the actual sorting process, we can notice how with each of the 6 clock cycles, the data become progressively more ordered. It begins as like a randomized sequence, form sorted subblocks during the intermediate stages, but at the end of stage 6, it resolves into a perfectly ordered sequence. And shortly after, our register write enable goes low, latching that final sorted data into the registers. So
Hi, my name is Yu Yingjie. Now I will explain the control unit modular. So to achieve the high throughput sorting, we adopt a design principle of control data path decoupling. By isolating the logic of state transitions from the actual data routine, we ensure that our design is not only modular but also highly reliable for timing closure. The heart of this modular is a mode-type FSI. As you can see from our code, it follows a deterministic six-stage execution flow. We specifically designed the state transitions to handle the Bytonic sort algorithm's complexity. We have one state to latch input data safely. Then it progresses through the stage 1 to stage 6. Each stage dynamically controls the routing of our parallel, compare, and swipe units by a 13 specific direction flags, the DIR1 through the DIR4. This allows us to reconfigure the data paths every clock cycle without requiring the external actual hardware area. Now moving to the verification. One critical challenge was preventing the pipeline deadlocks. If you looked at our downstage logic, we specifically programmed it to wait for the star signal to go low before returning to the IDLE. This prevents the FSM from accidentally retriggering and overwriting the sorted data. Our testbench simulation confirmed that the system effectively handled this edge case, ensuring a stable, deterministic sorting process every time. So in conclusion, the CU acts as the conductor, process conductor for our data path unit.